classes in classical mechanics. I don't remember, but it's a true theorem. It's a true theorem, and it's the reason that we here, in evaluating the gravitational field on this pen here, why we can pretend that all of the mass of the Earth is at the center of the Earth. When I evaluate the gravitational field here, keeping in mind that the Earth is a sphere, keeping in mind that it's pretty uniform and so forth, I can just pretend that all of the mass was at the center of the Earth. Until, of course, the pen hits the floor. Then it'll say, no, the mass wasn't, but until it hits the floor, pretend that all the mass was concentrated at the center. And furthermore, the masses outside, beyond this, even though there's a lot more out there, incidentally, there's a lot of mass out there. I'm not talking about the ceiling of the building. I'm talking about all the galaxies out there. There's a lot more, but the pen doesn't feel any. Only feels the things on the inside of the sphere. So Newton says, what I'm going to do is I'm going to take this galaxy, which is at a certain distance away. What's its distance here? Its distance is d. Its distance is the square root of x squared plus y squared plus z squared. X squared and y squared and z squared, that's the coordinates of this point over here, times a. The distance from the center. Can you read the, is it easy to read the red? I don't know why I started the red, I just lapsed. Is the red readable? Okay, fine. Square root of x squared plus y squared plus z squared, that's Pythagoras. And you multiply by a to find the actual distance. I can call that, let's call that d equals a of t, and let's just call this thing here r, capital R. R is not measured in meters, it's just square root of x squared plus y squared plus z squared. That's the distance from the center to the galaxy in question. Now, Newton's equations are about forces and accelerations. So the first thing is let's calculate the acceleration of x, of the point x, of the galaxy of the point x, relative to the origin. Well, first the velocity. The velocity, v is equal to a dot of t times r. And what about the acceleration? The acceleration is just differentiate again. Acceleration is equal to a double dot of t times r. Do we have to worry about whether r is changing with time? No, because the galaxy is at a fixed point in this expanding lattice. R is fixed for that galaxy, and so this is the acceleration. We could multiply it by the mass of the galaxy if we wanted to, but I don't need to. It's just the acceleration. And what are we going to set that equal to? We're going to set that equal to the acceleration that we would get from all the gravitating material inside here. Okay, so let's see how much. First question is how much mass is in there? Well, let's just call it the mass. The mass this is the mass that's inside this sphere. The formula that we're going to compare this with is Newton's gravitational formula. Force is equal to mass times mass. Which mass is this little one here? That's the galaxy. The mass of the big one, which one is that? That's all the mass on the inside. And distance between, well, the distance squared. And I'm missing a couple of things, two things I'm missing. Newton's gravitational constant, 6.7 times 10 to the minus 11th in some units. I'm missing one more thing. Anybody know what it is? The minus sign. The minus sign indicates that the force is attractive, pulling in. All right, that's the convention. Force pulling in is counted as negative. Force pushing out is counted as positive. All right, this is the force of gravity on a particle of mass m. What is the acceleration of gravity? The acceleration of gravity is just drop the mass. Just drop this out. To get the mass here, the acceleration is the force per unit mass, and write that this is the acceleration. M minus mg divided by c squared. That's the acceleration of that vector. What's that?
Which one is the small?
No.
Oh, okay.
No. No. I divided out the small m. Good. So that's the acceleration due to the presence of all this mass in the interior here. And that had better be equal to a double dot of T times R. God knows where this is going, but we're just following our nose, writing equations. And you know, that's always the way you do it. You start out with some physical principles, you write down the equations, and then you blindly follow them for a way until you need to think again. So we're on autopilot now. We're just doing equations. Let me rewrite it down here. A double dot R is equal to minus mg over t squared. Okay, let's plug in this guy over here. The distance is a times r. So maybe we can, maybe who knows? At some point we might have actually discovered something that looks interesting. At the moment it's just a blind a of t squared, or just a squared. Let's just call it a squared. A squared times d squared? No, a squared times r squared, right? Okay. Now, excuse me, but I'm just going to divide by r here. See, I secretly know where I'm going. Right. Maybe you do too, but that's all right. R cubed, I divide it, and I'm going to divide by another a. Makes this a cubed. Okay. Now, this is good. This will do. But next question: what's the volume of the sphere? Let's write the volume of the sphere. This is Newton's equations. Now, volume of the sphere. What's the volume? 4/3 pi. Now, is it r cubed? No. D cubed. Which means a cubed times r cubed. Right? Because distance is really a times r. That's the actual physical volume. When I say the volume, I mean the volume is measured in some standard unit like meters. That's the volume. Now look here, we have a cubed times r cubed here. Let me write that as volume 3/4 pi volume is equal to a cubed r cubed. Oh, maybe I'm being dumb. Maybe I shouldn't. Yeah, that's dumb. Let's not do that. Let's just look at this formula here. Notice that we have a cubed r cubed downstairs. Let's multiply by 4/3 pi, or divide by 4/3 pi, and multiply by 4/3 pi. 4/3 pi. What I did here, I undid here. But now I have m over the volume. What's m over the volume? The density. Ooh, something nice may be happening. A double dot over a is equal to minus 4/3 pi Newton's constant times the ratio of the mass in that sphere to the volume in that sphere. And that is the density. Now, that's a nice equation. Notice that it really doesn't depend on r anymore. If we know what the density of the universe is, and the density of the universe does not depend on where you are, the density of the universe does not depend on r, The left-hand side, r has dropped out. The right-hand side, no memory of r. It means this equation is true for every galaxy, no matter how far away. Same equation. Had we done a different galaxy, we would have gotten the same equation. The only way that this equation had any memory of which galaxy we were talking about was because of r. But r dropped out of the equation. That's, of course, a good thing, because if we want to think of A as something which doesn't depend on where you are, then it had better be that it drops out. So Newton confirms what he might have expected, that the equation for A is a universal equation for all galaxies. Yeah.
It seems like something seems a little off because we picked the origin and it was arbitrary, supposedly.
It was. Again, we would have gotten exactly the same thing no matter what origin we picked.
But I mean, it says whichever origin we pick, then we get the force going toward that origin. Right?
That's right.
Something doesn't add up.
Well, it has added up. But the answer doesn't depend on which. No, you have to. No. The point is, you have to do the transformation carefully. You have to do the transformation carefully. You go to another origin, and in your frame, Newton could have said, "Let me work this out from my frame of reference, which I will put myself at the origin, but let me study now the relative motion of some galaxies relative to some galaxy which is moving." He would have found exactly the same equations, but he would have had to do the transformation carefully. So we finessed that and got away from it by just putting ourselves at the center. But as you can see, the final formula doesn't care where you are. It confirms the fact that nothing really depended on which galaxy we thought of as our home.
But the direction of the force would. If we were really looking at the direction of the gravitational force, that's always toward the origin. Right?
There's a relative force. The right way to think about it is really a relative force. No, yeah. In this way of thinking about it, the force is always toward the origin, right? But had we stationed ourselves on some other galaxy that was moving and did all the transformations, remember, when you go to a moving frame, there are fake forces, inertial forces, fake forces that you have to add in. So from the point of view of this guy over here, this galaxy over here has a force which could be thought of as being toward here, plus a fake force, the fake force being an inertial force due to his acceleration. But we got around that by just saying, let's position ourselves at the center, no acceleration, no velocity, we just sit at the center. So the only question is, do we get an answer which doesn't depend on who we are and which galaxy we're on? Right. Okay, so that's part of the main message of this. The answer doesn't depend on which galaxy you're on, and so it really didn't depend on Newton's assumption that he was at the center.
Go back to the equation for mass. Would anything have changed if we assumed that nu was not constant?
Oh, yes. Yes, nu. Things would have changed if nu was not a constant. Made what happen? You mean a constant in space? Yes. To say that it's a constant in space is the principle that the universe is homogeneous. Absolutely. Everything hinges on the homogeneity of the universe. Right. The number of the mass per unit volume is the same everywhere in space. Yes, everything hinged on that. And okay, so here's one equation. It's a central fundamental equation of cosmology. And it's a differential equation. It's an equation for how A changes with time. Now, there's a number of things to look at, but the first interesting thing to look at is it's impossible to have a universe which is static. Static means that A doesn't change with time unless it's empty. Empty means rho equals 0. Only if it is empty, so if the side is 0, can the time derivative of A, or the second time derivative in this case, be 0? So, we derive the fact that the universe is not static. All right, one more thing we could do to make this an equation that we could solve is to replace rho by the constant nu divided by a cubed. Now, nu is literally a constant. It's the number of galaxies times the mass of a galaxy in a unit coordinate column. It doesn't change with time because galaxies are frozen in the grid. So we can write this equation one more step. A double dot. Not surprising that there's an A double dot. Why is there an A double dot? Because Newton's equations are about acceleration. And not surprising that there's an A double dot. Equals minus 4 over 3 pi times g times the density. But the point is now the density is not a constant. Nu is a constant, but nu over a cubed is not, because a is changing with time. And so we better put that in here. Nu divided by a cubed. Okay, so there's a lot of constants here. The minus sign is a constant. 4 pi over 3. G Newton is a constant. And we can pick nu also to be a constant. So everything out here is constant. A is not constant. But we have a kind of differential equation. It is a differential equation, a kind of equation of motion in terms of one constant, 4 pi g nu over 3. We have an equation of motion for the scale factor. For the scale factor, A is a function of time. Who was the first to discover this equation? It was actually discovered in the context of the general theory of relativity. It was discovered, I think Friedman, Alexander Friedman, before he got himself killed in World War I think, using the general theory of relativity. It's consistent with what Einstein should have done, but it's perfectly possible there's nothing in it that wasn't just good old Newtonian mechanics. Yeah.
Do you need to keep the A in the denominator on the left-hand side? Or
Well, I can multiply it if I like.
A double dot equals the constant over A squared?
Sure, you can do that. It's traditional to write it this way. It's just a tradition. Yeah.
So is that negative sign not tell us anything about whether we're expanding or contracting?
It doesn't tell us whether it's expanding or contracting. Okay, so let me explain why. Let me write, forget that now. Now we just have the Earth. Let's compare this with something else. We have the Earth, and we have a particle over here. Let's put it on the x-axis, All right, there's an equation for that particle. It's the same equation. Let's call it now, let's call it x, but x doesn't stand for these coordinates now. It just stands for the standard position coordinate, the height above the Earth. That satisfies some equation. X double dot is equal to the gravitational force, whatever the gravitational force is. mg over x squared minus, that's it, something like that. Okay, does this equation, what this equation tells us is that the particle is accelerating toward the Earth. The minus sign tells us that the acceleration is toward the Earth. But whether it's moving away from the Earth or toward the Earth is a question of velocity, not acceleration. Is the velocity that way, or is it that way? Well, you can imagine somebody over here taking this particle and ejecting it that way. It will have a positive velocity. It will be moving away from the Earth. You could also imagine the same person pushing it that way. It will be moving toward the Earth. X is decreasing. But the acceleration will be the same. In either case, the velocity will have a negative acceleration, which means if it's going this way, it'll turn around, or may turn around. If it's going this way, it'll increase the inward velocity. Whether it turns around or not depends on what?
Initial
And the initial conditions, or whether it's above or below the escape velocity. But in either case, the acceleration is toward the Earth. So knowing that the acceleration is toward the Earth, as it is for this pen, does not tell me whether it's moving up or moving down. It can move up and then move down, and you get the point. Okay. So no, this equation doesn't tell us whether the universe is expanding or contracting, but it tells us that the second derivative is negative. So it means that even if it's expanding, it's tending to slow down. If it's expanding, it's tending to slow down. If it's contracting, it's tending to speed up its contraction. There is an analog here of whether you are above or below the escape velocity, and we'll come to it. All right, so I was asked a question which I will just point out. Art, sorry Art, but I'm going to use your name. Art asked me, well, he looked at this and said, this is negative. And he looked at, what is this? He looked at this and said, this is positive. The universe is expanding, which is positive. How come this one's negative? But that's because he didn't read carefully. There's two dots here and only one dot here. This is velocity, this is acceleration. Not hard for acceleration to be negative. You know, you're in your Ferrari and you're going down the Autobahn or whatever. And, you press down on the brake. Your acceleration is negative, but your velocity is positive. You're slowing down, but you're still going ahead. Now, in fact, the universe is not slowing down. We're really doing what Newton would have done, and what all cosmologists thought the right thing to do was, until about 15 years ago. So 15, this is Newton's model of the universe, and it is the model that would have been called the standard model, close to it, the standard model of the universe, until the accelerated universe was discovered. This is the decelerated universe. The universe accelerates. So there's got to be something else in this equation. Well, there are several other things in that equation that will come to. Some parts do have to do with Einstein. Okay. Let's talk about not cosmology, but just particles, rocks, stones thrown upward from the surface of the Earth. Equations are very similar. But let's just examine them for a minute and take home a couple of lessons about it. Here's the Earth, and we might as well think of it as a point, because Newton proved the theorem that said we could think of it as a point. We're outside, we're above the surface of the Earth. So here's the Earth. Here's our particle over here. Put it over the x-axis. Put it on the x-axis. And what are its equations? The equations are Newton's equations, but there's actually a more useful version of the equation, which is just energy conservation. Just energy conservation. Let's write down the energy of this particle over here, and write down that it's conserved. In fact, it's a more useful equation than this one over here. The energy equation, more useful than F equals ma. What is the energy of this particle here? It's moving outward, it has some velocity. The velocity could be negative, it could be moving inward. But what is the total energy of this particle? The total energy of it is its kinetic energy plus its potential energy. Kinetic energy, 1/2 the mass of the particle, not the mass of the Earth, the mass of the particle times its velocity squared, which we could call x dot squared if we wanted. Well, let's just leave it as velocity squared for a moment. But what about the potential energy? Remember the potential energy? Potential energy is minus little m, big M, Newton's constant, divided by what? R, not R squared, it's R. Say it again. X, yeah, X. Now, this can be positive or negative, believe it or not. The energy does not have to be positive. For example, supposing this particle over here is at rest. I don't know how it got there. It got there, it's an initial condition. It got here at some time t, it's at rest, but at a positive value of x. X is really always positive. It really stands for the distance from the Earth, not from the x coordinate. So x is always positive. This is always negative. This can be 0 if the particle is at rest. So the energy is negative in that case. The energy can also be positive. Supposing we now take the same particle at the same position, but give it a velocity. If the velocity is big enough, then this can outweigh that. This can outweigh that simply when, if I write the equation down, I'll write it down in a minute, when this is bigger than this, kinetic energy is bigger than potential energy, then the total energy is positive. Now, if the total energy is positive, this thing cannot turn around. Cannot, might say, well, let's see, this particle can go out and turn around. Why can't it turn around if the total energy is positive? Incidentally, energy, of course, is conserved, so whatever the energy is at one instant, it's the energy at every instant. Energy is conserved. Let's suppose it turned around at that point. What would its velocity be at that point? 0. So what would its energy be? Negative. Right? So therefore, if it turns around, it's negative. The energy is negative. If it doesn't turn around, the energy is positive. Energy equals 0 is a sort of edge of parameter space. If the energy is positive, the particle just keeps going and going and going, it escapes. If the energy is 0, that's exactly the escape velocity. We'll ask later whether it escapes or not if it's exactly at 0. What is the escape velocity? The escape velocity is the solution of the equation that this is equal to 0. So let's write it out. 1/2 v squared. I'm dropping the m because it cancels from both sides. The little m. 1/2 v squared is equal to big M, big G, divided by x. And now we can just multiply by 2. And that gives us a formula for the escape velocity. That's the formula for the escape velocity when the energy is exactly equal to 0. In exactly the same manner, the universe can be above the escape velocity, below the escape velocity, or at the escape velocity. We're going to work that out in a minute. But all it means is if it's above the escape velocity, it means that initially, at some point, the outward expansion was large enough that it doesn't turn around. If it's below the escape velocity, then the universe turns around and recontracts. That's the main reason for showing you this. The escape velocity is kind of the edge. The escape velocity is also the velocity at which the energy is equal to 0. Keep that in mind. Escape velocity, same thing as energy equal to 0. All right, now let's concentrate on this particle over here. Now, for all practical purposes, this particle over here, all it knows is that it's moving in the gravitational field of a point mass at the center, where the point mass is capital M. So for all practical purposes, we can replace this problem over here by this one over here. In fact, it's exactly the same problem. So let's work out the energetics, the kinetic, the potential energy of this particle, and keep in mind that it's constant. It's constant because for all practical purposes, this particle is moving exactly as it would be if all there was a mass at the center, and in that case, energy would be constant. So we can just lift the things that I wrote before, but let's work them out. Yeah.
The capital M in this case changes as you move farther outside this.
No. No, the whole thing is growing, but remember, the grid, everything moves with the grid. Everything moves with the grid. The only thing that's changing is A. The amount of mass in the sphere stays fixed. In other words, the number of galaxies that this fellow over here sees within this sphere stays fixed. Right. Good. Okay, so we don't have to worry about the mass changing. All right, let's work out now the energy, the kinetic plus potential energy in Newton's frame. In Newton's frame, we'll work out the times. So what is it? It's 1/2 mv squared again. 1/2 the mass of this galaxy times the velocity squared, but that's a dot squared r squared, right? Same r. Same r, same r. D is equal to a times r. Distance is a times r. Velocity, a dot times r. This is 1/2 squared. And then minus little m, big M, g, divided by distance, right? Just divided by distance. That's the potential energy, M, g. And what is the distance? The distance is a times r, right? Let's do and that's equal to the energy of this guy here. That's its energy. Now, for simplicity, because simplicity and also because I'm getting a little tired, I think I will just do tonight the case where the energy is exactly equal to 0. What does that correspond to? Exactly the critical escape velocity. That case, the other case is just as easy, but let's do that case. All right, so that's the case where the universe is sort of just on the edge. Not clear whether it's going to turn around and fall back or whether it's going to keep going. It's on the edge of the cusp of doing one or the other. All right, so we're going to set this equal to 0. Let's work out that equation. Let's work out that equation using the various things we know. Okay, first thing to do is to get rid of the little m here. Why should we get rid of the little m? Because it appears in both terms here. All things equal to 0, so I divide it out. I'll also multiply by 2. Next, I'm going to divide by r squared. You know why am I dividing by r squared? I want to get r cubed down here because I know that r cubed has to do with the volume, and the volume, I'm going to get a density. I'm trying to get this thing a density. All right, so I divide by r squared, and that gives me an r cubed downstairs. That's nice because there's a mass here and an r cubed downstairs. It looks like I'm getting the density, but not quite, because the volume of the sphere is a cubed times r cubed, not a times r cubed. So what do? I I just divide the equation by another a squared. Okay, that's a cubed times r cubed. A cubed times r cubed. What do I do next? Well, if I'm smart, I will multiply this by 4 over 3 times pi. That'll literally make this the volume, but I'm doing something illegal unless I multiply it here also. 4 over 3 times pi. Equals 0, right? Equals 0. All right, we're almost there. Let me rewrite it. A dot over A squared. Remember what A dot over A is? It's the Hubble constant. So this is the square of the, I take it back. It's not a constant, the Hubble thingy. A dot over A squared, that's the Hubble thingy squared. And that's equal to, transposing this to the right-hand side, there's an 8 pi over 3, famous 8, 2 times 4 is 8, 8 pi over 3. There's a g. And now there's an m divided by the volume of the sphere. That's why I went to this effort here to put another couple of factors of a and r downstairs so that I would get a divided by the volume of the sphere, and that's rho. That's the mass density rho, the actual mass density. A dot over A squared equals 8 pi over 3 g times rho. That is the Friedmann equation. That's the Friedmann equation. The way that it's usually written. It's equivalent to this equation. This one over here is energy conservation, also set the energy equal to 0. This one over here is Newton's equations, but the same physics. The same physics, the Newton version of it, the conservation of energy version of it. This one is more useful. As I said, it's called the Friedmann equation. It's not completely general because we did set the energy to 0. We did set it to just exactly the critical escape velocity. So this universe is not going to recollapse, but it's going to... What does happen if you shoot something out at exactly the escape velocity? What happens to its motion as time goes on?
It's slowed to 0 at it.
Yeah. It just asymptotically gets slower and slower and slower. This universe will asymptotically get slower and slower and slower. Never seen. Okay, so that's our Friedmann equation. I'd like to solve it, but I don't know enough yet. The reason I don't know enough is because there's rho over here. I don't know what to do with rho, except we do know what to do with rho. Remember the equation, rho is equal to the constant nu. Incidentally, the constant nu can be set to be anything you want. It's the mass per unit coordinate. By changing your coordinates, you can change the amount of mass coordinate. So actually, nu never really changes. But rho is equal to nu divided by 8. So that. Okay, so we can now write an even more useful version of this. A dot over A squared is equal to 8 pi over 3 g nu, and nu is a constant. Nu does not change with time, divided by A cubed. All of this junk here is just a constant. 8 pi nu over 3 times g, just a constant. In fact, I could, if I like, have chosen nu so that 8 pi geo nu over 3 is just not the number 1. There's nothing interesting in it. The basic equation, the basic form of the equation is just that a dot over a squared is equal to some constant, but let's just choose that constant to be 1, just for simplicity, is 1 over a cubed. If we can solve this equation, we can solve this equation, we can solve this one. It's not hard to go from one to the other. So we'd like to see how to solve this equation. Now, notice, first of all, that the right-hand side is always positive. In fact, it never quite goes to 0. No matter how big a gets, it's always positive. As a gets really, really big, it gets smaller and smaller. So that tells us that a dot over a never becomes equal to 0. A dot equals 0 would be the universe turning around. That would be the place where the universe turned around when the expansion rate went to 0. So this tells us the expansion rate never goes to 0. Hubble constant never changes sign, or at least the square of the Hubble constant never goes to 0. So if it doesn't go to 0, it can't change sign. But it does slow down. The Hubble constant gets smaller and smaller and smaller with time. So it's as if the universe just gets tired of expanding. But it never gets tired enough to stop. We try to solve this. I think I will just take, it's getting late, I'm tired about this time. So I will take the easy way of solving it, but we will come back to these kind of equations. We'll come back to the, and this type of equation, this is absolutely, when I say not this type of equation is absolutely central to all of cosmology. We can solve it. Solve it quite easily. Let's just look for a solution of a particular type, okay? I'll look for a solution rather than to solve the equations. Let's see if we can find a solution where A is some constant times time to some power. We don't know that we can solve it this way, but we can try. We can take a trial solution. A equals A proportional to T would just, what would A proportional to T mean? That would just mean A grows in proportion to time in a very simple way. We don't expect that to be right. It's not, because the thing slows down. But we can look for a solution of this type. So let's try it out. Let's see if we can use the equation to see whether we can solve for C and P. Okay, so what's A dot? A dot is C, P, T to the P minus 1, right? That's just differentiation. Now, A dot over A, that's easy. We just have to divide by A, so we have to divide this by C, P to the P. C's cancel. Neat. Constant here cancels. And what's T to the P minus 1 over T to the P? P over T, right? That's the left-hand side. P over T, oh, sorry, we have to square it. This. P squared over T squared. That's the left side. P squared, sorry, P squared over T squared. Now, what about 1 over A cubed? Let's see what that is. 1 over A cubed, that's 1 divided by C cubed P to the 3P. Is that right? You do. All right. Now we can read off how to match the two sides. Let's get rid of this over here. Let's match the two sides. In the denominator, we have a power. We also have a power over here. This is 1 over t squared. This is 1 over t to the 3p, but I haven't told you what p is yet. So if we want to match, I've just said, let's look for a solution of the form c t to the p and see if we can figure out what c and p have to be. Well, the first thing we learn is that 3p had better equal 2. Otherwise, these things can't match. There's no way that t to the 4th here can match with t squared here. So the first thing we learn is that 3p has to equal 2. Come back to it in a minute. All right, that will guarantee that the t squared and the t squared agree on this side. On the other hand, we also have to match the constant, and the constant tells us that p squared equals 1 over c cubed. So that tells us there was really only one constant that we had to worry about, either p or c. Once we know p, and we do know p, we know p from here, and therefore we know the constant. The constant is not so interesting. What's interesting is p, because what does p say? It says that a expands like t to the 2/3. T is equal to 2/3. Some constant times t to the 2/3 power. That's the way a Newtonian universe would expand if it was right at the critical escape velocity. It would expand with a scale factor and everything, all galaxies separating as time to the 2/3 power. That's quite a remarkable derivation, I think. I think, Newton, I don't know why he didn't do it. Really, it annoys me that he didn't do it. Should have done it. I think he went to the mint. Oh, that was the year of the plague? No, it was the year of the tulips. He lost his shirt on tulips. Yeah. What? He did lose his shirt on tulips. Yeah. Yeah, he was one of the suckers who got suckered by the tulip bubble. That's true, right? So, smart. Hmm? Yeah, but I think he got stung.
Did Newton know there was a universe?
No, but he should have predicted that there's a universe. Oh, yes, he did. And he worried about the fact that a homogeneous universe, oh, yes. He most certainly had speculated enough that he was right on the threshold of doing this. He had asked all the questions about it and didn't quite carry it out. So, yeah. Yes, this is actually not. But, yes, that's a good question. Well, we've done a completely Newtonian theory. In Newtonian theory, space is flat. If space is flat, it just goes on and on forever. So yes, the Newtonian universe would have been infinite. It would have been spatially flat. It wouldn't have had an interesting Einsteinian geometry of any kind, although it would have been expanding or contracting. And it would have been entirely Newtonian. All right, so I did this just, first of all, because it's easy. Second of all, because it contains a lot of the physics that we're going to be dealing with in a simple form. And it gives us a model universe. It gives us a model universe with a scale factor that increases like the 2/3 power of the time. Yeah. Not quite, no. No, then there's another term in this equation. Another term in this equation. And we will come to that other term. No, it can't be, because if you had negative energy, it would recollapse. Right. So there's another term, and next time we'll take up that other term, and we'll talk about the three possibilities: less than zero, in other words, recollapse; greater than zero, that means the universe just expands without even thinking about it; and this which is the critical point where it slows down in a certain way. Another diagram that people always draw for this kind of thing looks something like this. You've probably seen diagrams like this. Plot the vertical axis, plot A, scale factor. And on the horizontal axis, you plot time. Now, A equals T. There's no sensible cosmology that does that, and let's just draw it in. Here's A equals T. Now, what does it mean that A decelerates? That the acceleration is negative? That it decelerates is a statement that the curve is bent over this way as opposed to this way. The second derivative is negative. The curve goes this way. A to the 2/3 looks approximately like this. And of course, it keeps growing. What about a recontracting universe? What if the universe recollapsed? A collapsing universe would look like crash, and this does not approach a straight line, incidentally. Okay, it does not approach a straight line. It just keeps bending over slightly more and more. And a universe of positive energy would look pretty much the same, and then go off on a straight line. On a straight line. Those are the three cases that we'll describe. Did I get that right? No, wait, I take this back. This is not quite right. I take that back. It's, no, that's incorrect. Well, we'll do the case of positive energy. But in any case, in all of these cases, the tendency is to curve over because the acceleration is negative. The real universe does not look like that. The real universe starts out looking like that, and then starts to curve upward. It's accelerating. The real universe is accelerating. Yeah.
So we got this C to try solutions in a certain
Because
form.
what?
Because we tried solutions in a certain form.
Yeah.
If we were to just sit down and experiment with other solutions to get the others, that we would have different results.
We'll solve the equation in detail, though. This is it. This is it. This is the solution. Yeah, we'll. Yeah. No, this is the only solution. Or we can change the energy. We can change the energy away from zero, and if we do, we can generate other kinds of solutions. Okay. Any questions? Tired? Yeah. No. Well, sorry. Yeah, the derivative gets smaller and smaller. 8 to the 2/3. All right, so let's see. What do we know? Yeah. No, we've already done it. Yeah. Let's. D to the 2/3 A, and A dot is equal to 2/3, 1 over t to the 1/3, right? So the slope goes to 0. The slope goes to 0 as t gets larger, right? But it's always positive. Okay, so this is the sense in which it's getting tired. The slope is yeah. And you can see now why Einstein failed to be able to describe a static universe. Well, we'll come to it. I'm getting ahead of myself. Yeah, I don't want to get ahead of myself. Okay, good. Let's.
Very old. If it was very old and the fusion
If it was what?
very old,
Yeah. I think that Newton was prejudiced. Yeah. Yeah. See, Newton had this idea that the universe was 6,000 years old, and this wasn't fitting together with this. Yeah. Newton was a believer. So I think he had some. I think the reason he probably didn't do it is because he couldn't make it fit with his prejudice about the age of the universe. It's true. What's that?
Did he write papers about his thinking and philosophy and stuff like that, or unfortunately, he did.
Yeah, sure he did. He wrote more about religion than he did about more about religion, I think, and alchemy than he did about physics. So, yeah, he's a prolific writer. Yep. Same 8 pi g. What's that? Yeah. Yep. Not surprising, since this is about energy. Yep, absolutely. No, this is the theory without a cosmological constant. The cosmological constant is what has to do with the acceleration. This is the theory without the cosmological constant. In fact, this is called a matter-dominated universe. Matter-dominated universe, for reasons that I will explain.
So, well, we know that the universe is expanding overall, like the entire universe. Are there some galaxies in between that could be contracting?
Well, certainly, yes. Yes. On the average, out to the largest observable distances, it is expanding, but individual little portions, there are places. For example, our galaxy is contracting together with Andromeda. Andromeda is not receding away from us. But that's on large enough scales. The Hubble law is not exactly true for all possible distances. It becomes accurate as distances get larger. It's certainly not accurate for the for things which are bound together. Things which are close enough together that they're really bound together by gravity or any other force, maybe being pulled together. So as it happens, it's not unique, but on the average, everything is moving away from everything else. But here and there, you can find galaxies which have peculiar motion. The term peculiar motion is a technical term. And it is. It's a technical term, and it means away from the average.
So in an overall calculation, we should avoid those little galaxies and just try and look straight past them.
We should average over large enough volumes that these little fluctuations don't matter. Right. It's the same kind of thing when you say the air in the air in the room is uniform. Well, that's not really true. There are places where there's a fluctuation where it's more dense and a fluctuation where it's less dense. But when averaged over a sizable region, bigger than many molecules, the room is uniform. Same thing holds here.
So you mentioned Andromeda. moving toward the Milky Way, is that just motion in an expanding?
Yes, yes, yes. The Andromeda just happens that for whatever reason, I don't know if it's really, I don't know if the complete history of the Andromeda Milky Way dynamics is however it was formed in a pocket which was dense enough that just slightly out of the ordinary, it was dense enough that these two galaxies had enough mass to overcome the effect of the explosion. So it's a fluctuation away from the one. No, they're identical. They mean the same. You asked me that last time. 7 years ago, I think you asked me the same. No, there's no difference. You see, you either take the position that the galaxies are moving away from each other, or you take the position that they're embedded in this grid, and the grid is expanding. It's a mathematical. Perhaps in Einstein's way of thinking about it, it's a little more natural to think of it as space expanding, but they are equivalent. Now, one more question.
Is there any corroborating evidence other than the brightness of the distant type 1a supernova for the accelerating universe?
Oh, yeah. There's yes, there is from cosmic microwave background. Yeah, there is, and we will come to it. Right. It's a sort of network of different observations. The supernova, mostly supernova, and cosmic microwave background fit together just precisely.
For more, please visit us at stanford.edu. Stanford University.
Let's review a little bit, and then I want to move on to generalizations of what we've talked about so far. I think we worked out the equations of an expanding universe. There were Newton's equations. Let's talk about something else first. Does Newton's equations really get it right? Yeah, Newton's equations does get it right for the most part, and let me explain why. Einstein's equations have to do with curved space-time. Now, the universe that we're ultimately going to study has curved space-time, all right, and in fact, some versions of it even have curved space. That simply means that space itself, forget space-time, just space itself, if you measure triangles on it, if you do various kinds of geometric exercises on it, you'll discover perhaps that space is curved. At the moment, it looks pretty flat, but it's possible that it will turn out on the average to be curved. And if it is curved, well, maybe it looks like a three-dimensional version, let's say, of a sphere. Well, we're going to study later, not tonight, maybe probably tonight, it's a portion of a sphere. That's a portion of a sphere. We're over here. We look out. We can only see so much. We can't even really see that the sphere is curved. But at a large enough distance, we may be able to see that the sphere is curved. On the other hand, supposing we just decide to look at very neighboring galaxies. Now, very neighboring galaxies can mean 1 billion light years from us now. Very, very neighboring galaxies, much smaller than what we think the radius of curvature of this universe is. Well, then it looks flat. And if it looks flat, it should mean that at least for that portion, if we're not interested in the whole thing, but we're just interested in the local nearby behavior, we should not have to worry about the fact that it's curved. If that's correct, that it means that the way these galaxies move relative to each other and how they move apart from each other, at least in the small here, can be studied using Newton's equations. That's what we've been doing. We've been looking at the universe in the small and studying how a small little fraction of it is expanding or not expanding, whatever it's doing. And it's perfectly legitimate and, in fact, entirely consistent with Einstein, with relativity, except for one thing. Except for one thing. We would run into trouble if the galaxies, or whatever is present, galaxies, particles, whatever is present, if they were really moving past each other with a significant fraction of the speed of light. One of the assumptions is that the neighboring things are moving relatively slowly with respect to each other. Something very, very far away may be moving with a large velocity relative to you, but as long as the things nearby are moving with non-relativistic velocities, you can study, relative to you, you can take a small patch of it. Now small could mean 10 billion light years, but you can take a small patch of it and study it without using any relativity theory. If we discover that there are particles moving with close to the speed of light past each other, then of course we will have to modify the equations. But there are particles moving fast by comparison with the speed of light past us. What are they? Well, neutrinos for one, but photons. Now I don't mean photons from the sun, I mean photons that would be there even if there was no sun. The universe is filled in the same way that it's filled with galaxies. It's also filled with radiation, homogeneous radiation. And that homogeneous radiation does move with the speed of light. That means that we have to modify our equations somehow to account for this very, very fastly moving, rapidly moving material, photons. We're going to do that tonight, but I want to just review what we did last time quickly. We first of all said, suppose that space is homogeneous and filled with galaxies, and I'm not going to try to draw all the galaxies. They form a gas, if you like, that kind of fill the blackboard with a certain number of particles per cubic meter. In other words, a density that we called rho. And that was the content of the universe in kilograms per cubic meter, if you like. You could use some other units, but whatever the units you like. Physical units, kilograms per cubic meter. And we called it rho. We laid down a grid on this universe. And laying down the grid, there was clear ambiguity. Imagine that we laid down the grid at some specific time, like today. We laid down the grid, and you could ask, what is the spacing between the grid was a coordinate system, let's call the coordinates x, and the distance between x equals something and x equals something plus 1. In other words, one grid separation here, one lattice separation, there's a certain distance associated with it. How big is that distance? Well, we called it A, but how big is A? That depends on the grid that we laid down. If we laid down a very coarse grid, it would be one thing. If we laid down a fine grid, it would be another thing. And so it had better be that our equations, at least at the moment, do not prefer any specific value of A. We could lay down a different grid. The different grid could be twice as dense. Here's the black forms one grid, and the black and green together form another grid. If we looked at the more dense grid, we would also invent an A, let's call it A prime. A prime is the distance between neighboring points on the dense grid. That would be 1/2 A. So if you ask me what is the value of A, I'm going to say I can't tell you until I know precisely what grid is laid down. And so A itself doesn't have a physical meaning, at least at this stage. Later on, we'll discuss more what A means. But at the moment, on a flat blackboard, it doesn't mean anything by itself until you specify exactly what the size of the grid is. Okay, so A is just sort of bookkeeping device. On the other hand, ratios of A may mean something. Let me give you an example. Supposing I told you, now A is a function of time. The universe is expanding. The distance between neighboring galaxies, the galaxies are embedded in the grid. They move with the grid. The actual physical distance between galaxies is growing. Okay. Supposing I told you that over a period of time, A doubled. That has meaning. That means the distance between every galaxy, every pair of galaxies doubles. So ratios of A, particularly ratios of A at different times, are recording a history of how the universe is expanding or contracting. And that's why our equations tend to only involve ratios of things with A. Let me give you an example. Let's take A dot, the time derivative of A. Well, that will depend on whether I use the black grid or the black-green grid. Every A associated with the black grid is twice as big as every A associated with the black-green grid. And if every A is twice as big, A dot, the time derivative, would also be twice as big. On the other hand, if I take A dot divided by A, and let's compare it with A prime dot divided by A prime, they will be the same. They will be the same because the ambiguity in the scale of the grid will cancel out. A prime will be a half A dot prime will be a half A dot, you know what I mean? And the factor of 2 will just cancel out. So things involving ratios of A, those are invariant, physically meaningful things. And if you remember, A dot over A is just the Hubble constant at a given time. So it really does mean something. But A itself, an ambiguity in how big it is, but it's a once and for all ambiguity. Once you fix it, then you stick with it. Okay, another thing which is ambiguous was we introduced a constant, nu. Remember what nu was? Nu was the mass contained within a single cubic cell of the grid. In other words, a grid element here, 1 by 1 by 1 by 1. Well, one what? One grid unit. The amount of mass within that cube, which we called nu, is ambiguous because we haven't determined exactly what the grid is. Nevertheless, once the grid is fixed, nevertheless, the amount of mass within a single cube is called nu. But it also changes when you change the grid. Now let's go to the equations that we derived last time. The equations we derived last time, I'll just remind you how we derived them. We took the universe filled with galaxies. We called them particles uniformly, and we placed ourselves right at the center, arbitrarily, but still consistently. We placed ourselves at the center, looked at another galaxy which was at a specific location on the grid, some x on the grid, and we studied Newton's equations for the motion of that galaxy, which you would think would be horrendously complicated because they're interacting with loads and loads of galaxies. But we used the famous theorem of Newton. Well, first of all, we imagined smoothing things out so that we could think of the distribution of these galaxies as smooth and uniform. We took a sphere, centered at us, Then we used Newton's theorem that told us that relative to us, in the coordinate system where we are at rest, the force on that galaxy only depends on the mass within that sphere, as if all of the mass were concentrated at the center. So we just said, let's concentrate all the mass within that sphere at the center, and then study how, under such circumstances, the galaxy at X would move if it were under the influence of just that mass. You don't have to worry about the masses on the outside, you only have to worry about the masses on the inside, and we worked it out. And the simple way that we worked it out, the simplest way we worked it out, was just to say, if there was a particle over here moving under the influence of a fictitious mass at the center, then the energy of that particle would be conserved. The energy consisted of two terms. Well, I think let me come back to the derivation again. I just want to review the derivation very quickly, but I'll come back to it in a moment. Let me remind you what the equation was. The equation that was derived was that A dot over A squared, that came from the kinetic energy, was equal to the density of matter, rho, measured in physical units, in other words, measured in kilograms per cubic meter, not this new object over here, but rho. And there was a little more. There was an 8, a pi, and a g Newton. That was the equation that we derived by just looking at the conservation of energy. Rho, rho. Oh, sorry, you didn't catch me. Over 3. That 3 ultimately came from the volume of a sphere, 4/3 pi r2. So the 3, the 8 is 2 times 4. Pi is pi, 3 to 3. This is related to the volume of some sphere. Okay, that was the equation that we worked out. That was in the case of zero energy. That was in the case where the potential energy of this point and the kinetic energy of it exactly cancel. It could also be understood as the situation where every galaxy is exactly at the escape velocity, just on the knife edge between being able to escape and not escape. That's what that formula was. We added one more thing to it, and the one more thing is we said that rho, which is the amount of mass, it's the amount of mass per unit volume, is related to nu. Is it the same as nu? No, because nu is the amount of mass per grid box. But the grid box, you don't know what its volume is. This is the mass within 1 cube. If you want the density, then the density is related to nu by dividing nu by the volume of one of these boxes. This is density per cubic meter. This is per cubic box. You divide that by the volume of a box, which is A cubed, and that's one more fact that we put in, that rho is nu divided by A cubed. Now, is rho constant with time? No, because A changes, but is nu constant with time? If nu just represents ordinary particles sitting in the universe which are never destroyed, never created, particles of protons, let's forget whether the proton decays for the moment. Protons are forever, and galaxies are forever for a moment. Not forever. We won't believe that forever, but we will believe for the moment that galaxies are forever. Did you get that? Yeah, okay. If galaxies were forever, or protons were forever, then nu would be constant. The number of protons within a box is the same at all times. All that happens is the box grows. So the protons thin out, but the number of them in a box stays fixed, and so nu stays constant. What is it? What is its numerical value? I can't tell you what the numerical value is because that has to do with the exact grid that I use. If I change grids, I change nu. Okay, so but in any case, once I've established all of the conventions, I can replace rho by nu divided by a cubed. Nu is a constant that doesn't change with time. 8 is a constant, pi is a constant, 3 is a constant, g is a constant. All of this stuff here is just a numerical constant. In fact, by judiciously changing your definition of the grid, since changing the grid changes the magnitude of nu, I can, if I like, choose 8 pi g nu over 3 to just be 1. It doesn't make any difference. The point here is that the numerical constant that appears here really doesn't make any big difference to the way the universe evolves. And the way you can see that is by changing definitions of the grid, you can change the constant. So we could, if we like, just set 8 pi g nu over 3 equal to 1, and then we would have a very nice differential equation. A dot over A squared is equal to 1 over a cubed. Now, would you like to see how to solve that? We solved it last time, but we solved it by guessing. How many people want to see me solve it in real time? I know when you want to see me solve it in real time because you're hoping I'll make a mistake. Yeah, you were going to ask a question. Okay. Well, it's too bad. I'm going to solve it whether you want me to or not. Here's the way you solve it. Here's the way you solve all these equations. You first of all take the square root of both sides. On the left side, that's easy. It's just a dot over a. On the right-hand side, it's a little bit of a nuisance. It's 1 over a times square root of a. Do you see where that came from? A cubed is a squared times a. The square root of it is a times the square root of a. Okay. Let's multiply both equations, both sides by a to get rid of it in the denominator. And that just tells us that a dot is 1 divided by the square root of a. That's where we would like to begin. Okay, now, we're going to write this, dA by dt, what it is equal to 1 over square root of a, but now we're going to do something tricky. The very tricky thing we're going to do is instead of thinking of a as a function of time, we're going to think of time as a function of a. We're going to take a to be the independent variable. And to do that, here is dA dt. That looks like a is a function of time and we're differentiating it. But if I turn it upside down, it's d, meaning taking 1 over it, it's dt dA. And now it looks like it's the derivative of time with respect to a. And that's equal to the square root of a. So how do we solve it? We look for a function of a whose derivative is the square root of a. What function has as its derivative the square root of a? 8 to the 3 halves, right? Well, 2/3 8 to the 3 halves. So we find out that t is equal to 2/3. The 2/3 is absorbed into other constants that we've been ignoring, times a to the 3 halves. All right, we can solve that now. What we really wanted was a as a function of time, but that's easy. If we just neglect the 2/3, I just don't feel like writing it. To get the 2/3, this tells us that a is equal to t to the 2/3. A is equal to t to the 2/3, which is a function a t, which looks like that. And it gets flatter and flatter and flatter. The flattening of it is deceleration. The universe is decelerating but it never comes to rest. We could see that it never comes to rest because when we look at this equation, there is no point at which a dot over a becomes 0. How do I know it doesn't become 0? Because the right-hand side is never 0. It gets smaller and smaller as a gets bigger and bigger, but it never goes to 0. And that's why the universe decelerates. Another way to see that it decelerates, it's just a particle moving away from a fixed force center. It will decelerate because of the attraction by the force center. And that was lesson number 1. Right? I redid it because, well, I always think it's worthwhile redoing most important derivations. Yes, it's okay to throw away the negative square root. What's the logic? The logic from the equation, you cannot tell whether the universe is expanding or contracting. Both are possible from the equation. If you start, it's exactly the same deal as saying you have a planet over here. Yeah, coffee is a good planet. Well, and the almond here is a rock. And you see the rock is right over here. The equations of Newton will not tell you whether the rock is moving away or whether it's moving toward. There's one thing you can be sure of. Let's ignore for the moment moving in orbit. Let's assume we know that the rock is moving radially. There's one thing we know for sure, that it's not standing still. It may be momentarily at rest. It might have come up and stopped, but it's not going to stand still. It's accelerating. It's accelerating back toward the planet. So it could be going out and decelerating, or it could be going in. You can't tell from the equation. The same way, you can't tell from the equation whether it's expanding or contracting, and that has to do with the two possible solutions, whether the ADT is positive or negative. If it's contracting, it's negative. If it's expanding, it's positive. Okay.
Excuse me. Sort of all these objects are kind of moving radially. So,
Yeah.
of course, I think of all these objects out there, they're all, kind of spinning around each other.
Well, okay, so that's right. That's right. But still, on the average, they tend to move as if they were embedded in this grid. Given that they are embedded in the grid, the only option they have is to move radially relative to each other. Now, you're perfectly right. There are motions on top of that average motion. The motions on top of the average motion don't, of course, satisfy this. They're called by astronomers peculiar motion, meaning, the sun moves around, the Earth moves around the sun, and the Earth is not participating in this expansion relative to the sun, but, if you go a few galaxies over, the whole thing is. So the real motion of real galaxies is a combination of this average flow. Think of it as a flow, a river going downstream. How fast is any given molecule moving? Well, I don't know how fast any given molecule is moving, but I do know on the average that clumps of molecules sufficiently averaged are moving with whatever the velocity of the river is. On top of that, there's the peculiar motion of the molecules relative to each other. So that's the way to think about it. A flow, and on top of the flow, fluctuation. And we're ignoring fluctuation at the moment. Okay. There's two directions I want to expand it. Well, not expand. There's two directions I want to generalize in today. The first, well, probably the second. The second will have to do with what happens if you replace massive particles, galaxies or protons and so forth, by photons, by radiation. How does this whole story look different? If there was a universe, a fictitious universe, which had nothing in it but photons, how different would this be? Now, why am I doing that? What a silly thing to do. Why take a fictitious universe which is only made of photons? Well, what we're going to find is that early on in the history of the universe, the most important thing in the universe is photons. Today, and when I say most important, I mean the largest concentrations of energy. Early on, the most concentrated, the biggest form of energy in the universe was radiation. Today, the most dominant form of energy in the universe is just the masses of particles, E equals mc squared kind of energy. That's what this theory is about. It's about the behavior of massive particles, non-relativistic, slowly moving particles. Yeah.
I thought today was dark energy.
That's also presumably made of particles that are pretty much standing still. Mm-hmm. Oh. 30 years ago, we would have sent it down. Right, we're still 30 years back, or 25 years back, or something like that. You're right, good. Yes. But dark matter, by contrast, is part of this story. So, yes, thank you, that was helpful. Yeah. Well, what I'm telling you now is an old story, but it's a story whose basics are important to us. Okay, two directions I want to go. The first has to do with what happens if the universe is made out of other kinds of stuff other than just particles more or less relative to each other, radiation in particular. And the other is to move beyond the assumption that the energy is zero. There was no reason for that. It was arbitrary. We said arbitrarily, let's assume that every galaxy is moving away with exactly the escape velocity. Let's back off that now. And how do we back off it? We go back to the energy equations and say the energy of that particle moving in the fictitious field, not the fictitious field, but the field of the fictitious concentrated mass at the center. This is not a real galaxy now. This is the combined mass of everything within the green sphere. Particle out here, moving outward, and let's apply the conservation of energy to it. Let's go back through the derivation, apply the conservation of energy, and then see how the equations change when we go away from the limit of zero energy. Okay, so what is the energy of this particle? This whole glob here has mass m. We'll come back to what m is in a moment. But as mass m, it's not the mass of the sun, and it's not the mass of any specific galaxy, it's the mass of everything in the sphere. Okay. And the energy of this fellow over here is 1/2 m. M is the mass of this fellow, not the big mass in here, the mass of this galaxy, times its velocity squared. That's one term. And then the other term is minus mg over the distance between them. Let's call the distance d as we did last time. Oops, I missed something, didn't I? Another factor of little m, right? Product of the masses, Newton's constant, distance between them. That's the energy of this particle moving out. And what do we know about it? We know that it doesn't change with time. It doesn't change with time because our model, that's a useful model, is just the motion of a particle in a fixed background of mass. The energy is constant, so let's set the energy to be equal to some constant. Now, what does constant mean? Does it mean a numerical constant that's independent of everything else? No, it doesn't. It could depend on which particle we're talking about. Could. In fact, if the universe is homogeneous and isotropic, the only real thing it could depend on is the distance away. So I'll simplify the discussion for now by taking this particle to be at x equals 1. In other words, we're going to take a specific particle, a very definite one, at x equals 1 and focus on it. It has some specific energy, and that energy will never change. So let's just call it E, and it's a constant. What value of the constant? I don't know. I can't tell you offhand. No more than I can tell you if I know that there's a nut over here and there's a planet over here, there's no way I can tell you a priori what the energy of that particle is. I don't know how fast it's moving. Right? So we have to study all possible cases. Right? So we just put the energy and call it E and take it to be a constant, a numerical constant. Let's write out now everything. Let's divide this. Let's first of all divide it by m, little m. Let's divide by little m, divide by little m, and then over here we get E over m. Now, E is a constant, m is a constant, E over m is a constant, so I really haven't made it any more complicated by dividing by m. I'll leave it here as E over m, but the right-hand side is just a numerical constant. Let's even do a little more. Let's multiply by 2. It's still just a constant, and since I didn't tell you in the beginning what E was, all I know is that this is a constant. So let's leave it that way. Now what about the velocity? If this is the galaxy at x equals 1, then its velocity, well, its distance, the distance is a times x. The velocity is a dot times x. And so now we can just plug that in here. And x is 1. I've chosen x to be 1, so it's very simple. The distance of the galaxy is just the scale factor a. It's called scale factor. And its velocity is just a dot. So let's plug it in here. This just says a dot squared minus 2mg over d, and d is a, is equal to some constant. Now I'm just going to call it c, constant on the right-hand side. This has many of the elements of this equation here, but this equation, this nice equation, we divided by a twice to get a dot over a squared. Why did I do that? Because I knew in the back of my head that a itself is not a meaningful thing. It's only ratios of a's. So in the back of my head, I knew that what I really want to get is an equation for ratios of a's, or a dot divided by a. So I divided this equation by a squared. A cubed. Notice something's happened on the right-hand side here. It's no longer a constant. C is still a constant, but a squared now has something new in it. And finally, we used that the mass divided by the volume cubed. Now, this is a sphere. This is a sphere of radius a. X is equal to 1. A sphere of radius a. And the volume of a sphere of radius a is 4/3 pi a cubed. So I have a cubed down here. That's not quite the volume of the sphere. Let's fix it so that it is the volume of the sphere. Let's multiply. Well, I don't want to botch up this equation too much. Let's rewrite it. A dot over a squared minus twice mg over a cubed is equal to a constant over a squared. But now let's multiply and divide by 4/3 pi. So this is 4 pi over 3. And we have to multiply out here by 4/3 pi. That becomes 8/3 pi. That's where our 8/3 pi came from. Okay, 4/3 pi a cubed over 3, that is the volume of the sphere. And what is the mass divided by the volume? The density. So by fiddling around, I got the Friedmann equation, but with a right-hand side now. A right-hand side that knows about the total energy. If C is positive, it meant the total energy was positive. It meant the kinetic energy outweighed the potential. Sounds like, and it does, means that the galaxies are going to continue to recede forever. You've beaten the escape velocity. If C is negative, then the energy is negative, more potential energy, more negative potential energy than kinetic energy, and that's the situation where you expect everything to go out a ways and then come back and crash. So we now have a new equation, the Friedmann equation for non-zero energy. The energy can be positive or negative. Positive or negative, both are allowed, total energy. And let's examine it a little bit and see if we can see a little bit what it says. It's not too hard to solve for any given case, but let's solve it. Oh, one other step. One other step. Right over here. E dot over A squared. And let's transpose this factor to the other side. Equals 8/3 pi g times rho, but rho is nu divided by A cubed. Remember nu? Nu was the mass per unit cell size. Nu over A cubed, that's rho, is g. G is there. Plus C over A squared. This is the new thing. C over A squared is the new thing that was not here in our initial study of this equation. What does it do? All right, so let's look at it first. This is the real Friedmann equation with this other term on the right-hand side. And it was derived from general relativity, not from special relativity. Sorry, not from Newton. But nevertheless, we just derived it from Newton. Good. Okay, so here we are. Let's see what these things mean. Let's assume for the moment that the universe continues to grow. If C is positive, and everything else on the right-hand side is positive, 8 pi g nu A cubed, they're all positive, then the right-hand side is strictly positive, and A dot over A is positive. In other words, the universe continues to grow. If A dot is positive and A is positive, if A dot, the time derivative of A, is positive, the universe continues to grow forever. It may slow down, but it will continue to grow, or at least it won't contract, and it will continue to grow. So if C is positive, the universe will continue to expand. It will eventually get arbitrarily big. By arbitrarily big, I mean that A will eventually exceed any bound and become very large. So let's look at it in the limit that A becomes much large, very, very large.
Why is A dot over A have to be positive? I mean, the square of it is positive.
Right. The square of it is positive. That's right. Good. The square of it has to be positive. So let's assume that initially it is positive, that the universe starts out expanding. Okay? Then the only way it can ever get to be negative is if it goes through zero. And it can't go through zero if the right-hand side is positive. Good. So that's a good point. The right-hand side being permanently positive disallows this from being zero, and therefore it can only continue to grow. It can't jump from positive to negative without going to zero, and this is never zero. Okay, now which term here is bigger? 1 over A squared or 1 over A cubed? Well, that depends on whether A is big or small. All right, but in particular, let's go and think about very large A. Let's start with small a first. For A being small, which is bigger, 1 over A cubed or 1 over A squared? 1 over A cubed. If you take A to be small enough, this will always beat this. And so for a sufficiently small A, this is negligible compared to this. We've already studied the case without this, and we know the answer. We know the answer as long as A is small, in other words, in the very early phases of the expansion, when A is just starting out growing, is just beginning to grow, this term is not important. And what do we find? We found out when the term was absent that A expands like t to the 2/3. But now let's go to the other limit. This is a standard way of thinking about all kinds of things. Go to limits. Often an equation, this equation is solvable, incidentally, but it's nasty. We don't have to solve it. We just have to know what it's doing at the two ends. The two ends mean when A is very small and when A is very big. Okay, so what about when A is very big? Which term is big? This term is the biggest term when A is big. 1 over A squared is much, much bigger than 1 over A cubed. You may have to wait a while, and how long you have to wait may depend on this constant here, but eventually this term will become much larger. So let's study that equation. Let's study the equation A dot over A squared is equal to some constant, any constant, over A squared. We first take the square root of it. And what's the square root of a constant? Another constant. So I won't change its name, but it's really, this new c here is the square root of the old c. And of course, the reason I'm allowed to do that is because it doesn't matter what the constant is here. We'll get an answer which